Good morning, everyone. Welcome. How's everyone feeling today? Are you excited? Okay, you can do a little bit better. Is everybody excited? Amazing. Thank you for joining us. So I'm excited today because I get to open this stage and I get to talk about AI. Everyone's favorite topic to talk about these days, right? I promise you that this talk is not going to be a bunch of hype. It's going to be some practical stuff that you can use in your applications and in your projects going forward. So we're going to talk about how you can optimize AI in some specific ways and how you can go from rag to riches. And that's going to make a little bit more sense in the next slide. But if you're completely new to AI or you're a veteran of an entire 6 months, you should get something out of this talk. So let's look at the agenda here. First of all, we're going to get a brief history of AI, and then we're going to talk about Retrieval Augmented Generation. We're going to look at search and retrieval in AI, and then how we can think of RAG as a recommendation system. We're going to kind of breeze through those topics really quick because those are the basics. And we want to get to the heart of this talk, which is optimizing for accuracy and cost. And so that is what the rag to riches comes from. How can we optimize your rag pipeline for accuracy and cost? So let's dive straight into it. There is a huge demand for building intelligence into our applications. And in order to make these modern, highly engaging applications, we can also make differentiating user experiences for each user. And so to compete and win, we really have to make your applications smarter and surface insights faster. And these AI-powered models can take autonomous action for our users. And the results are twofold. Firstly, we have these apps that drive competitive advantage by deepening user engagement and their satisfaction by their interactions in our applications. And secondly, our apps unlock higher efficiency and profitability by making intelligent decisions faster on fresher, more accurate data. And so almost every application going forward is going to use AI in some capacity, whether it's on the back end or the front end or both. And so building these, in order to stay competitive, we need to build these smart capabilities into our applications. And so there are many different use cases, but here's just a few. We have retail, healthcare, finance, and manufacturing. These are very different use cases, but they're all unified in their critical need to work with the freshest data in order to achieve their objectives in real time. But how did we get to this stage of AI? Let's look at a quick evolution of AI. So in the early days of computing, applications primarily relied on analytics to make sense of data. And so this involved analyzing large data sets and extracting insights that could inform business decisions. Now, as computing power increased, it became easier to analyze this data in less time. So the next stage is batch AI. As computing power continued to increase, then the focus shifted towards machine learning. And so traditional batch machine learning involves training these models on historic data and then using them to make predictions or inferences about future events, about how users might interact in the future. And so the more data that you fed it over time, the more accurate it can become, the more accurate these future predictions can become. And so you can imagine that this is really powerful because if you can predict what's going to happen tomorrow, you can make really good business decisions today. And so batch AI, as the name implies, involves running offline on a schedule. And so it's analyzing historic data to make predictions about future events. But that is where the problem is with batch AI. It can't react to events that are happening quickly in real time. And so this might be okay for certain use cases, but for the majority of our applications, we need to be able to react to things in real time. And so that's where the next stage came in, real-time AI. And so real-time AI really represents a significant step forward from traditional AI. This approach involves training models on real-time data, live data, and making predictions or inferences in real time. And so this is particularly useful for fraud detection, for instance, where the need for that real-time data is critical, because what good is fraud detection when the person defrauding you has already gotten away with it? And so the last stage brings us to generative AI, and this represents the cutting edge today. It might be something different tomorrow, who knows, but today this is the cutting edge. And this involves training models to generate new content. So this can be text, images, video, audio, and so on. And so it's not simply making predictions about future events anymore, it's actually creating the future. And a fun fact here, of course, DALL-E made all of these images. And so over the years, we've seen AI evolve from traditional analytics to real-time and now to generative AI. And each of these were not just incremental changes. These were transformative. They shaped the way that we interact with technology every single day. So it's good to understand where we came from and how we got to where we are now. And so let's go back to the meat of this talk. You've probably heard about this thing called generative pre-trained transformers, GPTs. So these are large language models that perform a variety of tasks, such as natural language processing, content generation, even some forms of common sense reasoning. And so these are the brains that make our applications smarter. But there is a catch. These GPTs, they're great, but they're not perfect. There are limitations, and one of the primary limitations is their static knowledge base. Now, we know that there are some integrations now that can allow them to search the internet for newer data, but how do we know that what they're finding on the internet is accurate? They can also hallucinate very confidently, and so how can we minimize that? And they can't access real-time proprietary data, your data. And that seems like a big limitation, don't you think? So the need for real-time proprietary domain-specific data is why we can't rely on the LLMs as they are. And so this is especially true in the business context, where up-to-date information is a game changer. And so what's the solution? How do we make sense and use these models and adapt them and so that they can have this real-time knowledge and align with our specific needs? Well, we're not merely going to leverage the power of these GPTs on their own. We're going to use them to take our applications to the next level by making insights and making them context aware. And so we're going to explore how to augment these LLMs with smarter capabilities, using these large language models to boost their capabilities that they already have. And so we're going to do that through Retrieval Augmented Generation. Now, a lot of you have probably already know about Retrieval Augmented Generation, and so at this point, we're going to quickly go through an overview of what Retrieval Augmented Generation is. So, first of all, it involves vectors. What are vectors? Well, these are the building blocks that allow us to represent complex, multidimensional data in a way that's easier to manipulate and understand. In the simplest terms, the vectors are a numerical representation of data, literally an array of numbers. So we have a quick brown fox, that text equals this array of numbers, and that is the vector representation of that text. And so these numbers are coordinates in an n-dimensional space, where n represents the number or the array length. So however many numbers you have in the array, that's how many dimensions you have. And so you might also hear vectors referred to as vector embeddings or just embeddings. And so here is a real-life example of vectors in use. You go to the store and you can't find something. You ask one of the workers, where can I find this? And they tell you, go to aisle 30, bay 15. That is a two-dimensional vector. And you also notice that similar items are placed near each other for ease of searching and finding. You'll notice like light bulbs, for instance, they're not strewn all around the store. They're strategically placed so that they're easy to find. And then video games. Video games use 2D and 3D coordinates to keep track of objects in the game world. And with these coordinates, we can compute proximity between objects and do collision detection, for instance. And so the same kind of math is used to compute the similarity between vectors during vector search. And then if you're a Stargate fan, the gate address is made up of at least 7 dimensions, and these are like vectors. And if you want to contact other Stargates, you can add an 8th or a 9th dimension, just like you would add a country code and an area code to a phone number. And so we can see how adding dimensions significantly increases the size of the virtual space that our data is organized in. And so again, what makes vectors so special? Well, they enable semantic search. In other words, they let us find information that is contextually relevant and not just keyword searches. And the data, it can be anything. It can be, it doesn't have to be just text. It can be images, audio, video, and so on. These can all be converted to vectors. But how do we go about creating these vectors? Well, this is done through an encoder. Encoders define how the information is organized in that virtual space. And so there's different types of encoders depending on your use case, and there's also different types of encoders for text, for images, for videos, and so on. So many of the popular encoder models can be accessed through Hugging Face, OpenAI, and many others. So what does this look like in practice? So first, we take our private data, our custom data, whatever it might be, and we generate our embeddings, and we store that in a vector database. And then, again, this data can be anything. It could be blog articles, it could be documentations from our website, it could be videos, images, PDFs, so many things. And once we have that, those embeddings in our vector database, we can then accept user queries to find relevant information from our custom data. And so to do this, we take the user's natural language query and we pass that through an LLM to vectorize it, because we need to put the user's query in that same virtual space as our custom data so that we can do that similarity search. So then we do that through vector search to find the most closely related, semantically related items, and we return those results. And we can do whatever we want with these results. Once we get them back, we can summarize the answer to the user's question. We can include links to some specific documentation, whatever might be applicable for that use case. And so with RAG and vector embeddings, your applications aren't just smart, they're adaptable, real-time, and incredibly context-aware. And so with this workflow, you actually have another advantage by using MongoDB specifically, because not only will you have your vector store there, you can also have your operational store, which can be used to enrich our queries even more, and we'll talk about that in just a bit. So far we've defined the basics of how RAG works, and so let's look at how search and retrieval, which is similar to RAG, how that has evolved in AI. So how did it start? Remember IBM Watson? So Watson got its fair share of criticism. It was pretty far ahead of its time, but IBM had the right ideas. They essentially combined search and retrieval with natural language processing to answer questions, which is basically what RAG is. And so the next evolution is virtual assistants. So virtual assistants, there are efforts underway to make them better, but as of today, so far, they've only been able to do a limited number of tasks because of search and retrieval. And so in most cases, these assistants retrieve and process data from APIs for common structured data sources like weather, weather services, calendar, map services, and so on. And so for everything else, the answer is, I can't help with that. And then came possibly the most successful use of search and retrieval in AI, and that was recommender systems. And so these are all over the place. They introduce you to new music. They introduce you to new videos. You have a For You page. They help your wife buy skincare products that she didn't know she needed. That's a screenshot from my wife's Amazon there. So these recommender systems are great. They're all over the place, and they use search and retrieval. And then finally, Retrieval Augmented Generation. This is where we use search and retrieval to get predefined large language models to answer questions about data that they were not trained on. And again, this is DALL-E's representation of RAG. So with that, let's look at how thinking of RAG as a recommender system for LLMs can help us to create a pipeline that gets you the most relevant information for generation. And so we know that our goal is to retrieve the most relevant document chunks from our knowledge base. But is it enough to just do nearest neighbor searches? Well, to answer this, let's look at how this would look like in a recommender system. Let's say that this system is going to produce product recommendations to our users. So yes, it could reduce the search space. But how about dropping out-of-stock items or items that the user has already purchased? It wouldn't be able to do that. And then how about predicting how likely the user is to purchase the items that we're recommending? It wouldn't be able to do that. Or how about ordering the items in a logical way, such as maybe ordering them by price point or genre or whatever the case might be? It couldn't do any of these things without additional help. So let's apply the same thought to RAG. If we use this one-step process here, again, we would reduce the search space, so that's amazing. But what if we wanted the LLM to generate answers based on the latest information or filter things based on latest information for like geographic location? It wouldn't be able to do any filtering there. Or maybe incorporate feedback from the user's previous conversations with the LLM. On its own, it can't do that. And even here, having the most relevant information near the top is important. There's been research that has shown that LLMs focus more on the beginning of their context window than the end when generating responses. And so if we use this one-step process, the order of results will be decided by the similarity score produced by metrics such as dot matrix, cosine, whichever you used. But this might not be the most optimal for our use case. So this calls for some additional steps. Instead of this one-step process, we could add a filtering stage. So this filtering stage, the filtering layer would only retrieve candidates that match certain criteria. And so this goes back to having your information, your operational data next to your vector data so that you can use that metadata in your operational store to do this pre-filter ahead of time. And then once we have that, we'll go ahead and do our vector search, retrieve the top K results using nearest neighbor search. And then let's add a scoring step. So this is where we can incorporate some user feedback possibly and do rescoring the chunks as well. And then finally, an ordering step where we might use a better re-ranking model. And that would allow us to, again, have the top results, the best results at the top of the LLM's context window. And so now that I've convinced you that we need a four-step system, let's dive a little bit deeper into each of those stages. So first we had the filtering stage. Let's look at that. Basically with filtering, we're basically trying to build an allow list to pass to the vector search. And so a filtered vector search increases accuracy and decreases computational load because we're not passing as much to the filtered vector search. We're filtering out a lot of that information beforehand. So again, it's more accurate and a little bit less of a computational load. And there is a little asterisk there, and the asterisk has to do with being too restrictive. And so it could possibly introduce hallucinations and some weird things. So the short answer is just make sure that you provide enough context and don't be too restrictive on your filter. And so, but why would we want to pre-filter? Maybe let's look at pre-filtering versus post-filtering. And so here we have a query vector and the vector similarity to documents in a movie data set. So let's say that our user has indicated that they only want movies with an IMDb rating greater than 7. So because we have this our operational data, which has that metadata in it, we're able to do that pre-filter on it and filter out the ones that have an IMDb rating greater than 7. And so if we apply this pre-filter and k is set to 2, which means we're going to retrieve the top 2 results, the vector search will exit as soon as it finds these 2 candidates. So, but after we apply, if we apply this as a post filter, though, then it would retrieve these 2 candidates. And the result of these 2, they are, the score of those is 0.95 and 0.92. So they score higher, but their IMDb ratings are less than 7. So doing that as a post filter, it would return those, but it would automatically drop them because they would get filtered out, and we would actually return nothing. And so with post-filtering, we don't get any performance gains, and we also run the risk of dropping perfectly relevant candidates. So pre-filtering is generally the way to go. So let's move on to our retrieving the top case similar chunks. And to look at this, we're going to look at some different methodologies for returning these. And so far, until now, we've only talked about vectors and vector search. But there's another common method called lexical search. And lexical search focuses on retrieving results based on exact keyword matches. And so vector search, like we just talked about, it retrieves based on similarity or contextual similarity. So you'd use lexical search when you know that your user's question or input is going to be an exact match to your search corpus. And you'd use vector search when you might have ambiguous inputs and you're not sure what the user might be typing in. And that way you can find things based on intent or meaning. So users interact with RAG systems such as chatbots via natural language query, and that could be very sporadic all over the place. It can vary a lot, and so getting documents with corresponding disjointed keywords would probably not return relevant documents. So, for example, with a full text search, if we search for "give me a recipe for apple pie," it might return search results for apple and pie separately. And so a strategy that looks at the query more holistically is necessary. So given our understanding of lexical search and vector search so far, it sounds like vector search is probably the way to go for RAG, which is what most of us use. So we'll go with that for now. But we have a small problem. While vector search would be better for accuracy, it also comes with a higher computational cost compared to lexical search. And this is mainly because of the performing distance calculations, which are basically matrix multiplications of high-dimensional vectors. And also having to keep these high-dimensional vectors in memory also costs us a bit more. And so this is just something to think about. So moving on, we have the next stage of scoring. So the goal here is to push that system more towards the right on the accuracy axis. And so one way to do this is by combining traditional keyword search with vector search, which is hybrid search. And so this way we can optimize for contextual similarity as well as important keywords. But how does this work? Well, again, let's take the example of our movie database. We could generate embeddings of the plot field, for instance, the plot text field. And we can create a vector search index on that. And then we could define a lexical or a full text search index on the text field. So we have our embeddings field and we have our text field, and we have indexes on each of those. And then we take our user's query and we perform we generate embeddings for the user's query and we perform our vector search. We also we return those results, and we also perform our keyword search and return the results for those. And then we can combine the scores generated from those and assign a final score. Excuse me, quick sip of water. And so once we have our final score, another thing that we can do is incorporate user feedback. So we could return the output of the LLM at the top there, and then also return the chunks that the LLM used to generate that response, and then incorporate a thumbs up, thumbs down system so the user could say, yeah, this chunk was good, it helped, it was very helpful, or it was not helpful. And then we could store this upvote, downvote information in our document. So again, having that operational store right next to our vector store is very helpful. We can store that information in that document and use this for boosting or suppressing these chunks in future queries. So for example, the number of upvotes would increase the percentage and downvotes would decrease by a percentage. So basically with hybrid search, we move the needle again to the right on the accuracy scale with a small uptick in computational load compared to vector search. So our last stage here is ordering. Let's take a look at this. The final push we see here to further improve our retrieval quality is ordering or re-ranking. And so you might notice that with every additional step, we've seen a slight increase in computational load. And this is okay to an extent because with RAG, our intention is to optimize these LLMs for accuracy. So we do have to take care of the computational load. Is not going to cost too much, but our goal is to make it more accurate. So if we didn't have a re-ranking stage, the order of retrieval is governed by the embedding model and the scoring algorithm, which aren't exactly optimized for relevance. And so a re-ranking model, which is a specific model that is trained to calculate the relevance between query document pairs, could be used here. So with the final re-ranking stage towards the end, you could be fairly confident that you're retrieving the most relevant information and putting it at the top of that context window again. And so that is the last stage of the four-step process to make your RAG pipeline more accurate. And finally, what we're going to look at is prompt compression. So prompt compression is the thing that can give us riches, sort of, not really. It's going to maybe save us some money. So there are many prompting strategies out there that have emerged, and some of them like in-context learning, chain of thought, and React prompting. But most of these prompting strategies involve composing extensive text to the LLM, otherwise known as prompt engineering. You've got these huge blocks of text that you're sending to the LLM. So LLMs with large context windows have been the new norm, and it's now common to see LLMs with an input size of 100,000 tokens, and in some cases 1 million tokens. And so that's okay for some use cases, but utilizing the full context window of an LLM through a REST API call can get pretty expensive. And so LLMs with large context windows, they have their place, but again, the operational costs can skyrocket pretty quickly. And so take, for example, paying $10 per 100 million tokens. Airbnb, for instance, they have several million users per day. And so they would have huge operational expense just from the volume of interactions that they have. And not to mention that there is also going to be increased latency in the responses because the LLMs have to process this large corpus of text. And then as you continue to build AI applications, you're going to come across the terms prompt compression and or otherwise known as token compression. So you might think during your building phase that you're not going to run into these issues. And during a prototype, you probably won't run into these issues, but it's important for us to think ahead. Think ahead of scalability and solve for these issues that could be bottlenecks in the future. So what is prompt compression? So prompt compression is the process of reducing the number of tokens fed into a large language model. So just making the amount of tokens smaller. So our goal here is to closely match the output quality compared to the original uncompressed prompt. So here's an example of an uncompressed prompt versus the compressed prompt. So the compressed text has the essence of the information from the uncompressed prompt. And the advantage here of utilizing prompt compression techniques lies in the ability to maintain the general information of the uncompressed prompt, but with a significantly less amount of tokens used. So one thing to bear in mind here is that prompt compression can suffer from information loss, especially with a large corpus of information where something is only mentioned one time, it might get left out. So this is something to be aware of, but generally prompt compression does a pretty good job. So prompt compression techniques can take us from 50,000 tokens down to 10,000 tokens. So this will provide the same length and quality of output from as from the original uncompressed prompt. And so with this method, we could save money by sending this fewer tokens to the LLM. And so what have we learned here? We've learned that retrieval augmented generation goes beyond nearest neighbor search. Choosing the right embedding model and pre-filtering that metadata can help us to reduce computational load from vector search. We can combine full text search, lexical search with vector search, also known as hybrid search. And then using re-ranking as a final step, we can find the most relevant results, make sure that they're at the top of that context window. And then lastly, carefully using prompt compression can make you rich. Not really, but it could save you some money. If you want to learn more about this, we have an article, What is an AI Stack? And it goes into much more detail on each of these and a bit more as well. I'll wait till the phones go down. And while you're doing that, everybody say AI. All right. And that's it. Thank you for your time. If you want to connect, I am Code Stacker everywhere.